to calculate Laplace transform and inverse Laplace transform. In the first half, I said, because we do not have specific formula for definition of inverse Laplace transform. So when we do the calculation, we need to calculate indirectly. So what's the meaning indirectly? So the idea is very simple. All right. Because we can calculate Laplace transform on a given function and get a different function f, right? Yeah. That's the direct calculation. But based on this formula and the definition of inverse Laplace, we can immediately write the inverse Laplace transform of capital F equals little f, right? Yeah. So we use this way, we can, calculate the inverse Laplace transform. Although no formula, right? Yeah. No formula for this. Yeah, but based on this calculation, automatically we have this. Okay? Yeah. So that's the indirect way we will use to calculate inverse Laplace transform. All right. Yeah. Linearity. Yeah. In calculation, we need to apply this linearity of Laplace transform a lot. When you apply Laplace transform on a linear combination of two functions, f function and a g function, you can separate. Okay? You can take constant out of the Laplace transform. A constant, B constant out of the Laplace transform. Yeah. Using the definition, integral definition, you can see this property easily. Yeah. All right. Now we are ready to calculate Laplace transform for basic functions. Yeah. All right. So next slide. So that Laplace transform of simple functions. Yeah. The first one, calculate Laplace transform of 1. Yeah. 1. F equals 1. Yeah. That simple function. Okay? Yeah. Now, so this is the definition of Laplace transform. Yeah. Think about, we replace little f by 1. So we just calculate integral of this e function directly. Then, yeah, because this one, although infinity thing, but we use limit to deal with the infinity. Yeah. All right. Yeah. So the formula, yeah, 0, infinity, because negative s times t, here you can see this s should be a positive number. Should be a positive number. If it's a negative number, think about it. If s is a negative one, negative s will be positive. Positive times t, when t goes to infinity, it's divergent, right? The function divergent. It's not convergent. The function diverges. The function diverges. Yeah. So you need to assume s must be a positive value. Yeah. Then you have this, yeah, because negative s times t, when t goes to infinity, e to a large negative infinity number, it's 0, right? The limit is 0. Yeah. So then you have 1 over s, because when t equals 0, you have 1 over s. E to the 0, it's 1. So 1 over s, but negative, negative, because this lower limit, you have a negative sign in front of it. So the answer is 1 over s, the first formula. Okay? Yeah. Laplace transform, basic function. Yeah. So this condition. Yeah. Second, now Laplace transform of e function. with a parameter A. Yeah. We just plug in, yeah. Two E functions we combine, right? Yeah. After combination, inside parentheses you have a S minus A. S minus A, you compare with this old formula, you compare it. So you can get 1 over S minus A. So S minus A, the whole parenthesis plays the same role as the S of that formula. So that's why you have 1 over S minus A. But the condition, S must be greater than N. S minus A must be a positive number. Yeah. That's the second basic formula. Yeah. So here, yeah. All right. The third one, here, cosine H. This function, we call a hyperbolic function. Okay? The cosine H function, we call a hyperbolic function. Yeah. Some of you may still can remember from calculus. Yeah, calculus, you already have more than two. Yeah. So here, I just recall cosine H of x equals e to the x plus e to the negative x over 2. That's the definition of the hyperbolic cosine. But the hyperbolic sine just minus, okay? X minus. Okay, all right. Here we apply Laplace transform on these two hyperbolic functions. L of, remember the linearity. This time we can apply the linearity property of Laplace transform. So we separate two terms. That two terms, we take constant out. Okay? Yeah. Then we apply that formula, right? Yeah. Apply that formula. So 1 over S minus A plus 1 over S plus A. Yeah? Right? Yeah. After simplification, we get this formula. Okay? Yeah. Hyperbolic function. Yeah. Right? Yeah. Second hyperbolic function, yeah. The only difference is we change the plus sign to minus sign. Okay? Yeah? Because the only difference is at that minus sign. Yeah. All right. Then after simplification, you get that representation. Yeah. Yeah. So that's the way here you get the idea. Now calculate the base. Then Laplace transform of cosine. Yeah. Here, so we calculate hyperbolic sine cosine earlier, because this sine cosine version of Laplace transform will be harder to calculate than those two. Yeah. So we calculate easier functions first. Yeah. Sine cosine relatively harder, so that's why we delay the calculation. All right. But to calculate that, we need to introduce a notation for it. Okay, symbol. L sub C cosine, the C. Okay, notation. And Laplace transform of a sine function, we use L sub S. Yeah. The reason is, when we do the calculation, when we represent the symbol L sub C, we get a formula related to L sub S. When we represent L sub S, we get a formula related to L sub C. Yeah? So that's why. So we need these two symbols to help us finally find the formulas of these two Laplace transforms. Yeah. Yeah? All right. Then we apply. First the definition, then integral by parts. Yeah, but limit. Okay. Yeah. Yeah. So then after simplification, yeah. So here you can see you have a L sub S. So L sub C equals this. Yeah. Yeah. So you need another equality, this time integration by parts, yeah, for L sub s. Yeah. After simplification, you get expression of L sub c. Yeah. Right? Yeah. So then you need to apply these, you know. So you have a linear system, actually. Yeah, but simple linear system. So you can find L sub c, L sub s easily. So L sub c, now you have this formula. Yeah. Yeah. Just do some simple calculation. Yeah. L sub s, you get this version. Yeah. Right? Yeah. That's number 6. Number 7, monomial. Laplace transform of t to the n plus 1. Monomial. Okay? All right. To calculate this one, we need a recurrence relation. Recurrence relation. Right? Yeah. So we apply the definition. Yeah. Definition. Integration by parts. Yeah. So you know, calculate carefully. Integration by parts. Yeah. That version. But the first term is gone. Can you see the first term is gone? Yeah? Why? Because at infinity, this e function, negative infinity, although this t goes to infinity, this t term also infinity, but exponential term dominates polynomial term, right? Yeah. Exponential term grows faster, yeah, because this negative exponent, you put the e to some infinity number at the denominator, right? So you compare numerator t to the n plus 1 infinity over determinant e to the s times t, also infinity, but exponential function increases much faster than polynomial term. That's why when you take the limit, yeah. If you want to calculate, that's easy. Yeah. Apply the L'Hopital's rule, yeah. You can prove it. Yeah. Yeah. But in that way, you can see this first term, 0, both 0. Okay? At infinity 0, at 0, 0. And 0 because this t term is 0. This e term 1. Yeah. This t part 0. 1, 0. Yeah. Also 0. Yeah. So this, you know, whole first term gone. Yeah. Then you only have the second part. So that's because this integral, another Laplace transform expression, right? L of t to the n. Yeah. So you have the recursion. Yeah. So you keep doing the recursion. So at the end, you have a final formula. Yeah. 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 So that's the formula number 7. Yeah. All these formulas very useful. Basic formulas. Yeah. All right. Yeah. Then so here we summarize it. So we have this table. Yeah. Most of them we calculated in the previous slide. But there is one special one we didn't calculate in the previous slide. Look at the formula number 5. Formula number 5, t to the a. Here, a is a positive number, but could be non-integer. And in the previous slide, we calculate t to the integer. That's this one. But if the exponent number is a non-integer number, then the calculation is not that easy. So we need to introduce a special function called a gamma function. In calculus, yeah, so you can see that gamma function, capital gamma function. That gamma function, why people introduce a new symbol, gamma, to represent this function? Because its explicit formula is very, very complicated. Yeah. So it's hard to write its explicit formula. So the gamma function is given with the integral format. So what's the gamma function? That people can write it in integral equals some integral expression. But expressive formula could be very complicated. So here we use that gamma function. Okay? All right. Gamma function. Yeah. So let's study the gamma function a little bit. The definition of gamma, this is the definition of gamma function. So integral. Yeah. But it's hard to calculate this integral. Yeah. So that's why explicitly, if people want to calculate this explicit integral, yeah, very complicated. Yeah. It's possible, yeah, but you need to use infinite series. Yeah. So the answer will be some infinite series. Yeah. Too complicated. Yeah. So then people just use this integral form, yeah, gamma, and they use a special symbol, gamma function represented. Yeah. Here, when you calculate integration by parts, you get a recursion formula. Okay? Yeah? Yeah. Because another gamma function. Yeah? All right. So this is your recursion formula for gamma function. That mu, nu, any real number greater than -1. Nu, right? Yeah. But the special case, when nu equals non-negative integer, yeah, yeah, you have the factorial. Gamma function equals factorial. Yeah. If the nu is non-integer, greater than -1, non-integer, it's not factorial, right? No. Because there is no definition of factorial. What's the definition of factorial? Non-integer. Factorial of a non-integer number. No definition. No such definition. Okay? Yeah. Here you can see the gamma function, basically, it is an extension of factorial. Okay? Extend the factorial to non-integer numbers. Yeah? Yeah? Factorial of positive integers, you can understand easily. But factorial for non-integer number, you cannot define. Yeah. But here there is a reasonable gamma function represent that. So, all right. So that's the way you view it, this gamma function. Yeah. And in many engineering problems, this gamma function is useful. Yeah. Yeah. Because people can use computer to calculate gamma function. If you really need a value of gamma function, you can use computer to calculate. Yeah. All right. Yeah. So then, yeah. So this one we did before, the formula number 7. Yeah. Here, actually, we just did it another time. Yeah. Okay. Yeah. So for this one, so yeah. So we can. We don't need to spend time on this one. Yeah. We did it before. Yeah. All right. Next one useful property when we calculate the Laplace transform. First shifting theorem. Yeah, we have two shifting theorems. First, second. So here, the first one. Yeah, shifting. All right. This is the definition of Laplace transform. Now, replace S with S minus. This is a shifting operation, right? Yeah. So what do you mean shifting? Yeah. This from S to S minus A. That is a shifting operation, right? Yeah. Along x-axis, you shift A units to the left and to the right. Yeah. So that's the reason So we call it shifting. Okay? Yeah. Shifting means this shifting. Yeah. All right. Then, so let's plug in. Yeah, because you need to plug into the formula, right? So f of s minus a, so you need to replace the formula in the original formula s by s minus a. S minus a. S minus a, you can separate, right? Yeah. So the exponent number you can separate. E to the negative st and e to the at. Yeah. But e to the at, yeah, you can treat e to the at times little f as a new function. How about that? Yeah. So this whole expression, you treat it as a new function. Okay? If you treat it as a new function, then this form, if you compare with the definition, you just get the Laplace transform of this new function, e to the at times little f. Yeah. So this, you get a first shifting theorem. This formula is called first shifting theorem. Yeah. Because in our later calculations, many times we need to use this theorem. Okay? Yeah. Yeah. So here. Yeah. So you shift. So here, at the end. Yeah. So how do we understand this formula? When we use it, so we need to. Oh, where is my? Oh, yeah. Yeah. So when we need to use it, so we use this capital of s minus a equals L of e to the at times little f. Yeah. So, yeah. So, yeah. We connect. Yeah. So, you can use both ways. Yeah. So you have little f. So that, because if capital F for this little f is known, then we multiply e to the at to the little f, and that side you just do a shifting operation on your capital F. You get the answer. First shifting operation. Okay? Yeah. So usually people use this way. Yeah. Okay. Yeah. Yeah. When you multiply e to the at to that little f, okay? First, you ignore, right? First you calculate Laplace transform of little f without e to the at. Yeah, you just calculate it. So you get a capital F function. Then you put it back, e to the at, you put it back, and that side you do a shifting operation. Yeah. So that's the way you apply this theorem. Yeah. All right. Then, so we write. Yeah. So here there are two versions. Yeah. The first version, yeah. So that's the, whatever. But second version, yeah, because you can always apply inverse Laplace transform. Yeah. So that's another direction you can apply this shifting theorem, first shifting theorem. Okay? All right? Yeah. So, yeah. Yeah. Because sometimes, here, sometimes you already know, yeah. So when you apply this theorem, both theorem, you already know the Laplace transform of the little f function equals capital F function. Okay? You already know it. Yeah. Yeah. Then, but sometimes you need to calculate inverse Laplace transform of capital F of s minus a. Okay? Yeah? Yeah. Then, this side, you just use this e to the at times little f. Yeah. Okay? Yeah. Yeah. And this way, yeah, because in this situation, you can calculate. Yeah. So for this situation, yeah, many times people just calculate. Yeah. Because many times when you calculate inverse Laplace transform of a function with a shift, yeah. So that's the situation. People apply this formula. you need to calculate inverse Laplace transform of some capital function with a shift, okay, minus a, plus a, sometimes plus minus, you just control the sign. Yeah. All right. Then the way you do, you calculate the inverse of f of s first. Okay? Yeah. Without shift. Right? Without shift, you have f of t. Then, after you find little f, then you apply this formula. You just put an extra e to the at in front of little f function. Yeah? So, these two ways you apply this theorem. Two directions. Yeah. All right. Yeah. So you need to practice. Yeah. Practice a few times. Yeah. So you can. This formula. Yeah. Very useful. This theorem. Yeah. Very useful. Then. Yeah. So let me show you one example. Calculate inverse Laplace transform. All right. We need to use this formula. So I put here our formula in our table. Number 7, cosine. Yeah. All right. And the number 11, here we need to use these two formulas. Oh, yeah. Actually, here I want to explain. Yeah. In this formula, how do you get? So from formula number 7, how do you get formula number 11? By the first shifting formula. Yeah. Yeah. Can you see it? Yeah. All right. So number 11, you can see that little f function, we just multiply e to the at. Yeah. Then when we take a Laplace transform, we should apply the shifting operation on that capital F of S, right? Capital of S. Yeah. So shift by A, so you replace S by S minus A. Yeah. S minus A. Yeah. Yeah. So just straightforward way to apply the first shifting theorem. Yeah. Yeah. Replacement, right? Yeah. Simple replacement. Yeah. All right. Then, another one from formula 8 to formula 12, another shifting operation, right? Replace little s by s minus a. That's simple. Okay? Yeah. All right. Then, now let's calculate. So this time, given, Laplace transform of little f, the capital F of S function given, we need to calculate little f, inverse Laplace transform. Yeah. So here, to calculate, to this calculation, can you, because this S, can you represent this expression using these two formulas? If you can, then you can apply formula number 11 and number 12. Okay? Yeah. So here, you need to do decomposition. Yeah. You need to do decomposition on this capital F of S function. Okay? All right? So let's do it. Yeah. Step by step. Yeah. All right. First, the numerator function, the denominator function. Yeah, denominator function. Denominator function, yeah. So here, so we just rewrite it this way. The denominator, can you see some special structure of the denominator? Right? Yeah. Can you see s squared plus 2s plus 1? That is the complete square. S plus 1 square. Then 400. 400. Then, because you have a s plus 1 corresponds to s minus a, right? A is negative 1. Okay? S minus a a, when a is negative 1, it becomes s plus 1, right? So you have s plus 1. So the numerator, you want to make that s plus 1. Yeah, s plus 1. Yeah, same a. Okay, numerator, denominator. So first you need to write your capital F of s in the special structure. That's the first step. After the first step, linearity, remember that? Linearity property of inverse. Inverse will also have linearity, right? Yeah. Laplace transform will have the linearity property. Inverse we also have Laplace transform, linearity. Yeah. All right. But before so here, so we write it in two terms. That's the linearity of the inverse Laplace transform. Yeah. Linearity. Yeah. Both the directions, linearity. Okay. All right. So we write, because, So the first part, constant out. Second part, because this omega equals 20, right? So for this second formula, numerator, we need to put the omega 20 there. Okay? Then you take constant 7 out. Yeah? So you write these two expressions. The first expression, you can apply formula number 11. The second expression, you can apply formula number 12. Okay? Yeah? Then apply it. Apply the formula number 11. You have this 3 times e to the t. Why e to the negative t? Why? Because e to the a times t. What is a? A is negative 1, right? Yeah. A is negative 1. S minus negative 1. S plus 1. So a is negative 1. So e to the at, so e to the negative t times cosine of omega t. Omega is 20. Omega is 20. Okay? Yeah. All right. So the second term, minus 7 times e to the negative t cosine omega t, 20. That's the way you calculate inverse Laplace transform. Yeah. Try to, adapt your mind to this kind of thinking. Yeah. So you need to think in this way. Okay. Yeah. Yeah. The calculation. Yeah. All right. So that's our this example. Yeah. All right. Yeah. Yeah. So the final answer. Yeah. All right. Next, existence and uniqueness of Laplace transform. Yeah. So there is some condition. Yeah. Yeah. This time we want to know a little more, because not all functions have Laplace transform. Some functions may not have Laplace transform. Okay? Yeah. So certain conditions should be satisfied. Yeah. Although that condition can cover large number of functions. Yeah. Yeah. That condition. But we still need to check that condition sometimes. All right. Existence theorem. Yeah. Why we need to know existence? Yeah, because sometimes the function, if it does not have Laplace transform, we cannot do it. You cannot take Laplace transform. All right. Yeah. After we find a solution of an ODE, we can verify it to see if the solution is valid. So here the argument is like this. Yeah. Some people may argue in this way. Why you need to check if Laplace transform exists or not? Because you just apply it. Apply it, whatever it is. Yeah. So you get something that could be a valid solution, or it may not be a valid solution. But you can verify it all the time, right? After you get something, yeah. If it's not a valid solution, then you plug in, so you can find it. Find it out. Yeah. All right. So that's the argument. Yeah. Help us understand Laplace transform. Yeah. Yeah. Although that's true. Yeah. Some people. Yeah. Yeah. But to know that. Yeah. Because that condition is not complicated. That condition pretty simple. We can see that if a given function has Laplace transform quickly. Yeah. With that condition. Existence theorem for Laplace transform. If f of t is defined and piecewise continuous. Piecewise continuous. You see here the condition. Piecewise continuous. Yeah. Not necessarily continuous, but it can be divided into several pieces. Each piece is continuous. Then you connect those pieces. Yeah. Piecewise continuous. Or every finite interval on the semi-axis t greater or equal to 0. Yeah. Semi-axis. Yeah. No negative side of the axis. No. Yeah. Because Laplace transform is defined on the semi-axis, right? Yeah. T greater or equal to 0. Yeah. All right. And satisfy 2. Yeah. Here, I need to give it. Yeah. So here the piecewise. This graph showed what's a piecewise function. It's like several pieces. Piece 1, 2, 3, 4. Okay. Piecewise. All right. And 2. Yeah. So here the condition 2. What is the condition? This is the main condition. You need to check if you want to see if this little f has Laplace transform or not. See? Capital M, some constant. Capital M and K, if the absolute value of this function is bounded by capital M times E function, e to the k times t. Yeah. Here you can see this bound is pretty large. This is an exponential function bound. Yeah. Yeah. If your f function can be bounded by certain exponential function, then it has Laplace transform. Yeah. So this simple condition, you can see quickly, right? Yeah. Yeah. So then the Laplace transform exists for all s greater than k. Yeah. So from this existence theorem, you can see if your little f function is not too bad. Yeah. Too bad, so that means it's growing even faster than that e function. Yeah. For example, yeah. So think about. So there is a function e to the t squared, right? That grows much faster than e to any kt, right? Yeah. So this function, growing too fast. Yeah. So then you cannot take Laplace transform. Yeah. Out of bound, right? If you take Laplace transform, the integral does not converge. The integral, because this function, break the kernel quickly. The kernel negative st, but this t squared, quickly dominates that kernel part. So then growing too fast. So in your integral from 0 to infinity equals infinity. Diverge. So it does not exist. Yeah. Cannot be too bad. Yeah. Your little f function. Yeah. So that's the, yeah. So here just show you, how to see that bound, right? Yeah. Show you, because you can, take absolute value. Yeah. This one, because now you replace its upper bound. Yeah. Upper bound, then because the upper bound bounded by this function. Yeah. Yeah. That means Laplace transform of little f is controlled by some function. Okay? Yeah. it does not diverge. Okay, diverge. The integral exists. Yeah. So this formula, this inequality tells us the integral exists. Integral exists. Yeah. All right. Yeah. Uniqueness. Yeah. Existence. Uniqueness. Yeah. If two continuous functions have the same transform, yeah, two have the transform, they are completely identical. Yeah. Same Laplace transform. Yeah. Two continuous. Yeah. But the condition is here. The condition is two continuous functions. All right. Yeah. Yeah. You need to make sure. Yeah. These two functions both continuous. Yeah. Think about if they are not both continuous, if they are both piecewise continuous. Yeah, let me say in this way. If both functions are piecewise continuous, can you say, if they have the same Laplace transform, can you say they are the same? Piecewise continuous, but not continuous. Continuous, no problem. Okay? Yeah. But piecewise continuous, then you may have problem. Yeah. Because at those discontinuity points, these two functions may not be equal. Discontinuity. You have discontinuity. May not be equal. Okay? Yeah. Yeah. But at the continuous piece, yeah, each piece, they are the same. But at discontinuity points, they could be different. Okay? Yeah. So this condition, yeah, make sure, yeah, when you apply this uniqueness result, pay attention to this, continuous requirement. All right, yeah. So let me stop right here. Yeah. So next time, first we need to complete this part. So then we will, learn some more. Yeah. Because we need to apply Laplace transform to solve ODE next time.